Hi, everyone. Can you see me?
Yes.
Okay, great. The cancer treatment has experienced 3 revolutions. It started with more than 70 years ago, the development of cytotoxic drugs that work by killing the fastest growing cells. However, this type of therapy cannot kill the last cancer cell without killing the person, because cancer cells are not the fastest growing cells in our body. The second revolution was marked by the development of targeted therapies that inhibit pathways that cancer cells are addicted to. However, cancer cells can always evolve to be addicted to something else. So drug resistance inevitably occurs. The third revolution is marked by the development of immunotherapy. And perhaps it's best publicized by this example. This is President Jimmy Carter, who is shown here posing for his 90th birthday. Soon after, he was diagnosed with stage 4 melanoma. The cancer was discovered during a routine checkup in his liver and in his brain. He thought he had weeks to live. The only thing he could do was to pray. However, he was put on an experimental drug being developed by Merck at the time called immune checkpoint. And he was miraculously cured. He was among the 20% of very lucky few who have melanoma. Because of this breakthrough, James Allison and Tasuku Honjo shared the Nobel Prize in 2018 for their discovery of the fundamental molecular mechanism of how cancers put on brakes on our immune cells, and also for their proof of concept development of treatment that unleash the brakes. They're called checkpoint blockade. However, checkpoint blockade does not work for breast or pancreatic cancers. In 2017 alone, we've lost 2 brilliant scientists, mentors, and friends at Stanford, 2 breast cancer and pancreatic cancers. I wasn't planning on sharing this personal history of myself. However, I was inspired by the previous speakers, Stuart, and the other talented speakers. I think that my story will inspire everyone in the current time where we all face uncertainty and despair. I myself was diagnosed with breast cancer in 2012. And I decided that I will not dwell on fate that I cannot control. Instead, I will work on things that I'm empowered to change. So when I was being wheeled into the surgical room, I was talking to my surgeon about how umecomab is actually a TLR7. It's not a TLR7 agonist. It activates inflammasome. And when I was waiting in infusion rooms, I was often either typing a cover letter to the editor saying that human thing needs to be activated, or writing on an NIH grant, which I would not hear about for another year. I decided that the more uncertain I am about my own future, the more I want to work on something big, something that takes longer with bigger impact. So I decided to ask why checkpoint blockade does not work on breast cancer and pancreatic cancers. Now the field acknowledges that perhaps part of the reason is that only tumors that already have T cells infiltrated in them, that you can use checkpoint blockade to unleash the T cell's power to directly kill cancer cells. However, most tumors are what we call immunologically cold tumors. They're simply quiet and do not have much T cell infiltration. So the idea is how everyone is trying to figure out how we can turn cold tumors hot. And I thought, let's activate the innate immune system because the innate immune system is our first line of defense against any invasion, including cancer, and it is upstream of adaptive immunity, namely T cell. So the specific questions we ask are, what is the danger signal secreted by cancer cells and that is detected by our innate immune system? And how do cancer cells disguise themselves from innate immune detection? And can we blow cancer's covers? So the answer now lies in this pathway. Through a decade of intense research by many labs in the field, we now know that cancer cells, for various reasons, have double-stranded DNA in their cytosol, where it should not be. Double-stranded DNA should only be in the nucleus or in mitochondria. So when it's in the cytosol, it's considered by our innate immune system a danger signal. Our innate immune system then makes a second messenger called a cyclic GMP-AMP, or cGAMP for short. The second messenger, this beautiful molecule, once made, then activates a powerful downstream effector protein called stimulator of interferon genes, or STING for short. STING activation then leads to production of interferon, which itself is a potent cytokine and also recruits downstream T cells. So I had the hypothesis, if STING is a powerful anti-cancer pathway, can we use cGAMP, its natural ligand, to activate STING? The problem is all second messengers are short-lived because their degradation and synthesis are tightly controlled. So as a chemist by training, I made the first contribution by making this molecule stable. And this molecule became the prototype of Novartis and Merck's experimental drugs that are currently being tested in clinics. Then I started my journey at Stanford Biochemistry and CAMH. There, my lab, Sabrina and Daniel, discovered how cGAMP and its analogs activate STING. They discovered that STING forms a polymer once activated, and this polymer is key for its downstream adaptor protein function. And to a chemist like me, when I see polymer, I see a chain reaction. I see an irreversible event. So once STING is activated, there's no going back. As a result, you only want to activate STING in the tumors. When STING is activated at places where it should not be, we have trouble. STING activation in the heart, or in the skin, or in the brain is a cause of heart attack-induced death and inflammation in lupus, Parkinson's, and multiple sclerosis. Systemic STING activation by a mutation causes a hyperinflammation disease that leads to early death in children. As a result, STING agonists, when being tested in clinics, are all directly injected into the tumors. This limits the type of patients we can treat. So is there another way? A second contribution I made was to identify the first, and to this day, the only hydrolase of cGAMP, called ENPP1. And this not only did not solve the problem, but started a bigger puzzle. This is because ENPP1 is an extracellular enzyme, while cGAMP is an intracellular second messenger. I had a wild hypothesis, and that is cGAMP is exported out by cells to function as an extracellular messenger. And Stanford Biochemistry and CAMH believed in me and recruited me to test this hypothesis. Jackie Carrozza in my lab used a hardcore analytical chemistry using tricks that we are also familiar with. She developed isotopically labeled internal standards and built cell lines as tools to show that in perfectly intact cancer cells where you do not see cell death, these cells are pumping out cGAMP as a soluble molecule. And if you remove this soluble molecule from a tumor, radiate tumors can no longer be cured, suggesting extracellular cGAMP is how ionizing radiation exerts its curative effects in this tumor model. So now we know that cancer cells cannot help but constantly make cGAMP due to their cytosolic DNA. And then they constantly pump out cGAMP to the tumor microenvironment. We asked, how does a host recognize extracellular cGAMP? Now, through Anthony and Volker's work, we know that many innate immune cells are the first responders, including macrophages and monocytes. They take up cGAMP, then produce interferon to recruit the downstream T cells into the tumor microenvironment. And that's how you turn cold tumors hot. My lab then collectively identified the first 3 transporters these first responders use to take up cGAMP, ranging from a known transporter to orphan transporter to ion channels. So now, starting from a picture that the field built, and starting from a hint that as a double negatively charged molecule, cGAMP can cross the cell membrane, I built the first non-hydrolyzable cGAMP analog, and my lab understood that it activates STING by triggering polymerization. I identified the first hydrolase of cGAMP, which turns out to be an extracellular enzyme. And that started the observation that cancer cells use various exporters to pump out cGAMP to get rid of it. And then host cells use cell type specific transporters to take in to fight cancer. So now this started the paradigm that cGAMP is an immunotransmitter, and it's very locally produced by cancer cells in the tumor microenvironment. So that is a danger signal cold tumors send out to the host to be detected, except they're smart. So some tumors overexpress ENPP1 to chew up this danger signal. This is how they disguise. So we blow their covers by developing ENPP1 inhibitors, which now can treat notoriously cold breast and pancreatic cancers in mice. So now with this, and with many labs who are working on the forefront of innate immune signaling, we are leading the 4th revolution in cancer treatment. Thank you.
Thank you so much, Lingyan. Is that moved over to me? I don't think so. Oh, it is. Okay, there we go. Thank you. I think I'm getting a little bit of a delay. My apologies. Thank you so much for that great talk, Lingyan. I learned so much, and I appreciate your personal story. Thank you for sharing that with us. I wanted to ask, you've identified ENPP1 as this potential drug target. Obviously, STING has become this really hot area of drug discovery. You talked about how one of the compounds you made was the inspiration for things that are now in the clinic. Are you yourself entrepreneurial? I mean, do you think that you'll at some point start a company around that target or something else?
Lisa, thank you for the question. We have spun out a company that are now developing ENPP1 inhibitors, and right now it's in preclinical stage. This will be the first of many companies that I probably will start, because I do realize that to translate from bench side to bedside, we do need much larger resources that academics can have.
So I wanted to ask you, you kind of started from this point, I think, in your postdoc that kind of unraveled into your lab, and you keep finding new questions that really open up big new areas of science. Do you think you're going to stay in this kind of immuno-oncology space? There's certainly no shortage of questions, but what's next after ENPP1?
That's a great question, and it's a hard question to answer now. To be honest, I am torn between two models. As a chemist, my projects had changed more often than now. And now when we're working on immunotherapy, we realize that it really takes decades of research. You not only have to identify the molecular mechanisms, but also have to develop the prototypes of therapeutics that as proof of concept. Otherwise, no one would believe you for decades.
Yeah. Well, I really, again, I'm seeing a lot of comments on here that are more comments about how much everyone enjoyed your talk. So thank you so much, Lingyan. We were so pleased that we got to learn about your research today. Thank you.